We'll start with oscillations. First, we'll describe what we mean by an oscillation. We'll talk about some examples and applications of things that oscillate, because oscillators have a huge number of possible applications in science and engineering and life in general. We'll give a mathematical description of oscillation without damping, and then oscillation with damping. Okay, what is an oscillation? This is perhaps the simplest oscillation we can think of. It's a mass on a spring. The mass moves, and the spring provides a restoring force. There is some equilibrium position around which this mass is oscillating. So this is like the canonical, simplest example of an oscillator that we can think of. This is a different kind of oscillator. This is a quartz tuning fork. This is what you have in watches. Until the 1950s, this was the most accurate timekeeper in the world. But if you have a phone or a watch, this is an oscillator that is used to keep time in that device. Phones these days update the time by referencing to the mobile network, which is then referenced to the GPS system. But this is the local timekeeper in these devices. It's also an oscillation, but rather than being just a single mass on a spring, now we have two masses oscillating in antiphase to each other. It's the two parts of this tuning fork that oscillate. This is another oscillation. This is an oscillation of the sun. So the sun's a big ball of plasma, and it deforms and wobbles, and this is a single, what we call a mode of oscillation. We'll return to the concept of mode later in the course. It oscillates at a single frequency. In this case, the period is 31 minutes, so it's a very low frequency oscillation. But nevertheless, we can write down an equation that describes this oscillation. It's the same equation that describes the oscillation of a tuning fork or a mass on a spring. It's just a single frequency oscillator. There are so many different things that oscillate. So for example, we have masses on springs, we have swings, the sun, the ocean with the tides, musical instruments. We have electronic oscillators, LC circuits, so inductive capacitive oscillators, quartz crystal clocks like the quartz tuning fork I showed you, AC current. We have quantum oscillations with light and atoms. We have biological oscillations with neurons, circadian rhythms, predator-prey cycles. There are so many different things that oscillate, and many of them can be described with a very simple equation. Now, there are applications of oscillations. Obviously, timekeeping is probably the most important one from the perspective of physicists. So pendulum clocks, quartz clocks, atomic clocks, these are all things that oscillate, and we use the oscillations as the tick-tock of a clock. The faster the oscillation and the higher the quality factor of the oscillation, and we'll return to the concept of the quality factor later, the better the clock you can make. So atomic clocks are the current state of the art because they have very high frequency oscillations, some of them into the optical sort of frequencies, and the precision of those oscillations, the frequency certainty of those is very, very high. To tune a radio station or a mobile phone network or whatever it is, then you need clocks and oscillators that run at particular frequencies. So mobile phone networks, the 4G networks, use 700, 900 and 1800 megahertz. Oscillators allow you to tune into these and generate signals at these frequencies. Precision measurement. So a really great example of how an oscillator is used for fundamental physics is finding the gravitational constant, big G. This is a really important constant, but it's also rather imprecise. So these are some experiments that are used to measure big G. This is one that uses a pendulum, and there are two pendulums here that swing backwards and forwards, a laser that measures the position of the pendulums, and then you can move some masses around and see how these pendulums are affected by the positions of the masses. So you can move them over here and you can move them inside, and by measuring changes in the frequency of these pendula, you can hope to determine the value of big G. This is a different kind of pendulum that also measures big G. In this case, it's a torsional pendulum. So we have a thin bit of Y here, and things spins. It spins around, it oscillates backwards and forwards in a rotational degree of freedom. And again, you have some masses that you use. You move the masses around and look for changes in the frequency. So by measuring the frequency, the period of these different pendulums, you can hope to measure the value of big G. How well are we doing? Well, this is sort of where we're at the moment. These are values of big G measured with different kinds of pendulums. So we have torsion balances, so they're rotational pendulums, simple pendulums. There's one which uses an atom interferometer. That's a bit different, but you can see all of these other data points here come from measuring the period of a pendulum. So this is all based on simple harmonic motion. One of the things that strikes you about this data is that there are lots of different data points that do not agree with each other. Finding big G is a really difficult experiment to do. It's every time you have electrostatic charges or magnetic forces, in addition to the gravitational forces, then you end up with systematic errors that can make some of these experiments very hard. And the problem is that gravitational forces are much smaller compared to magnetic or electrostatic forces. Okay, so the simplest oscillation, we have mass on the spring. Let's do some maths on it. So here's a spring, we've got the mass moving backwards and forwards. The force due to the spring is equal to negative kx. So x is the displacement of the mass from its equilibrium position at x equal to 0. So if we move the mass away from equilibrium, there's a force pulling it back towards equilibrium, which is why it's negative kx. That's Hooke's law. And we have Newton's law as well, which is the force is also equal to mass times acceleration, acceleration being the second derivative of x. So we can equate these force due to Hooke's law and the mass times acceleration. Note on the notation here, x double dot is the second derivative. The differential equation of motion equating these two forces here is that the second derivative of x is equal to negative k divided by m times x, where m is the mass of the oscillator. That's our differential equation of motion. This is the simplest equation we have for harmonic motion without damping. So there is no loss of energy in the system. It will in principle oscillate forever once it's set in motion. Now, how do we solve it? Well, let's do it with a sinusoidal function. There's our equation of motion. We're going to try the solution some amplitude, so that depends on how far you pull it away from equilibrium, and then it's going to oscillate as a cosine function with some phase phi. We can substitute it into the equation by finding the first derivative and the second derivative, and then substitute the second derivative here back into the equation and the zeroth derivative into the equation on this side. We find these two things are equal provided omega squared is equal to k divided by m. So there's omega squared there's k divided by m. As long as those two things are equal, then the left-hand side equals the right-hand side, which means that under this condition where the frequency, because omega is a frequency, the frequency of the oscillation is equal to square root of k on m, then this is a solution to the equation. So we can substitute root k on m here for the frequency omega. Great, so we've solved our differential equation of motion. We've found the frequency of oscillation in terms of the physical parameters of the system, because the frequency of oscillation is the square root of the spring constant divided by the mass. Great. But there are other functions that solve this equation, and it turns out these other functions are easier to use when these oscillations get more complicated, when we start to have damping and driving and all the rest of it. So sinusoids work, but the maths can get incredibly messy. What's this other function of which I speak? Well, it's using a complex exponential. We take the solution that looks like this, so we have some amplitude again, but instead of a sinusoidal function, we have a complex exponential. We take first and second derivatives, substitute the second derivative back into this side and the zeroth derivative back into this side, and we get exactly the same solution as we had before. And the frequency is the square root of the spring constant divided by the mass, and the displacement here kind of looks the same, except now instead of a sinusoidal function or a cosine, we have this complex exponential. The other thing we notice about it is that x in this case seems to be imaginary. As time progresses, we're going to get complex numbers. And that doesn't sit quite right, because we know that we can measure the position of this mass with a ruler, and the ruler only has a real axis, there's no complex axis. So what have we done wrong? Well, so the way to make everything real is just to take the real part. So we take the real part of the complex exponential solution here, add the curly r, meaning we're taking the real part here, add the real parts, and then the solution in the end is the real part of this complex exponential, which is the cosine component. And so when we use a single complex exponential like this, it's implicit that we only mean one part of it, i.e. the real part. But what you can see is we don't need to include this curly r all the way through our derivation. We can just do all of the horrible looking maths using complex exponential notation. But then before when we get to the end, before we write down the final solution, we just remember that we have a real valued function. We take the real part, and there's a solution to our equation. So there is another way of doing it using complex exponentials where the real part sort of falls out a bit more automatically rather than having to enforce the thing using the curly r. So here's our solution again as a complex exponential, but this time I'm going to write it as b, where b is now a complex number, equal to a times e to the I phi. So we've taken the complex exponential here and included it in a complex factor out the front. Now we can do exactly the same process here where we substitute it in and use the derivatives, and we find the same value for the frequency. But now when we take the square root of k on m to get omega, we're going to take the positive and negative square roots seriously. Now we could have done this before, but it wouldn't actually make any difference. We still get the same solutions, just we've kind of over-specified the solution in that case. But here we're going to take it seriously, and that means we actually end up with two possible solutions, two different complex exponentials. One, we have the positive root, and the other one, we have the negative root. And these two functions, one with a positive imaginary exponential, the other with a negative imaginary exponential, both solve the differential equation. So we must take a linear combination of this function and this function with different amplitudes out the front, because it's a linear combination of the two. So this function here will solve the differential equation. But we know that we want a real valued solution, so now we just say, well, b2 must be equal to b1 star. We must have that the factor out here is the complex exponential of the factor out here, and now we see that this complex number here, whatever it is as a function of time, is being added to its own complex conjugate, which means that this whole function here must be real valued. And so this is actually equivalent to writing down a cosine function. And you can go back and solve for what a and phi must be equal to in terms of the real and imaginary parts of b1, if you wish.